Alright, let us continue from last time. We were talking about subgroups and stuff. So, what we're building up to is the second isomorphism theorem. So, I'll just call isomorphism theorem 2, electric boogaloo. And so the setting is this. We have a group G, we have a subgroup H of G, and we've got a normal subgroup N of G. We proved that Hn and Nh are equal, and it's a subgroup of G. We've got H as a subgroup here, and N as a normal subgroup here. And then H intersect N is a subgroup of both of these. And normality holds here. And so we've got this normality here and this normality here. So you might wonder what the relation is between these two and these two. And the statement is that H mod H intersect, so that is not how you write an intersection. H intersect N is isomorphic to Hn mod N. So if you take this quotient, then it's isomorphic to this quotient. Okay, so let's prove this. Our previous results, and this is important, ensure that this makes sense. Because what we're saying is that these are group isomorphic, meaning that this is a group and this is a group. And these can only be groups if this is normal in here and if this is normal in here. And that's exactly what we proved last time. Okay? So let I be the map from H to Hn be inclusion. So if we have an element H, then it's going to get sent to just H times E, where E is the identity in our group G. And phi from Hn to Hn mod N be the natural map. And by that, I just mean that Hn, so no. So little h little n is going to get sent to little h little n big N, this coset. This is a little weird because n is an element of big N, and so that can get absorbed to there, but let's just leave it like that. Let psi from H to Hn mod N be given by composition. So psi is just going to be, let's see here, it's going to be phi of I. So phi or phi, whatever. I use phi and phi interchangeably, I think. I don't know. I don't really listen to myself talk that much. But, so phi of I. So the inclusion map is going to go from H to Hn, and phi is going to go from Hn to Hn mod N. So this whole thing goes from H to Hn mod N. So, let's see here. We want so we want a bijection. We want an isomorphism between H mod H intersect N and Hn mod N. So we want psi to be surjective, and we want the kernel of psi to be H intersect N. Because if we have both of those, then we can apply the fundamental theorem of group homomorphisms. I think this is like the second isomorph. Well, Okay, yeah, obviously this is the second time in a row we've used the fundamental theorem of group homomorphisms, because these are the isomorphism theorems, and isomorphisms are homomorphisms. But it just goes to show you, we throw around the fundamental theorem of group homomorphisms all the time, which is why it's called fundamental. So anyways, let's state that. What do we want? We want psi to be surjective, and we also want, I lost my place on the page, and now I have found it. We want the kernel of psi to be equal to h intersect n. Okay? So for surjectivity, for all hxn in hn mod n, hxn, now remember I said that we can, clearly we can absorb that in here. So x is in n, so we can absorb that, so this is equal to hn. But what is hn? This is just what happens when we take psi of h? Right. Okay, because what happens to psi of h? Psi of h, we're going to start with h, and then it's going to go to h times e, the identity. And then that's going to go to h times e times n, which is just hn, which is exactly this. And so this is equal to psi of h. So psi is surjective. Should probably write the word is. But anyways, so that's that. So next, we're going to let h be an h. What are we trying to do? Right. So if you take an element of h, okay, right. So we want to now we want to deal with the kernel. We want to prove that the kernel is h intersect n. So obviously the kernel is going to be h intersect. You can write it as, I don't know. If you start with any element here, then it's in the kernel if and only if what? Here, let's write this a little nicer. For all h in h, h is in the kernel of psi if and only if psi of h equals the identity e, and this is the identity in hn mod n. But what's the identity in hn mod n? We're modding out by n, and so this is just n. Okay, so psi of h equals n, but remember, psi of h is hn, so this is if and only if hn equals n, if and only if h is in n. But remember, h is obviously going to be in capital H because we chose it there. So h is going to be in n if and only if h is in h intersect n. So hence, by fundamental theorem of group homomorphisms, we have the desired result. And yeah, after this we're going to move on to more stuff, so I'm just going to go ahead and erase this, at least that part. So hence, by the fundamental theorem of group homomorphisms, we have h modded by its kernel is isomorphic to its image, which is all of hn mod n. And so there we go. That's exactly what we wanted to prove. And now we're done with isomorphism theorems. And we can move on to other things that are not isomorphism theorems. And let's see here. One thing we're going to start with is now we're going to talk about semi-direct products. So, sort of changing gears here, but sort of not. And you'll see why. So the definition, a G is G is the semi-direct product of H and N, and we write that in a sort of a strange way. We write it as G is equal to H and then this strange, kind of like a alpha but angular, I guess. So H semi-direct product N. Let's see here. If H needs to be a subgroup of G, N needs to be normal in G. We're not quite done. Hn needs to be equal to G, which contrasts with previously we discussed that Hn is just the subgroup of G. It doesn't need to be all of G. And the last thing is we need H intersect with N is trivial. There's sort of like a idea of like this is sort of like you see semi-direct product, so you're thinking direct product. This is sort of like taking a product of H and N, but and it's sort of like that because like you have this H intersect N is trivial, which is sort of like what you have when you take direct sums or whatever. I don't know. There's you can really get into sort of building an intuition as to why we came up with this definition in the first place, but I'm not going to go into that. At least not now. So let's see here. So see here, note if G is the semi-direct product of H and N, then the isomorphism theorem number 2 reads, well, we have H mod H intersect N, but that's H intersect N is the identity, and if you mod out by the identity, you're just left with the group. So it's just H is isomorphic to Hn. Well, we know Hn is equal to G, and so that's just G. So this is H is isomorphic to G mod N. So that's sort of neat. Also, so here we have 1 going to N, going to G, going to H, going back to 1. So N is I, this is I, and this is J of pi. So this is a short exact sequence. And let me explain what these things are. I is the inclusion map because let's see here, we know that n is a subgroup of G, and so we can just map every element of n to itself, and that gives us a homomorphism, and it's injective. Yeah, it's injective. Certainly not surjective. Yeah, so for this to be a short exact sequence, yeah. Then, of course, normally what we have is so actually we should write this as so, because what happens is if we have a normal subgroup, then typically we have 1 going to n going to g mod n going to 1 is a short exact sequence. That's something that we discussed not too long ago. But here, because h is isomorphic to g mod n, we can put h here instead of g mod n. And let's see here, what else do we have here? Pi is the natural projection. So I'll just write that down. Pi pi goes from G to G mod n, and that's just a projection map. And then here, let's write this h is isomorphic to G mod n. We're going to write this as G mod n can map isomorphically to h by some function, we'll call it j. So the second isomorphism theorem reads that h is isomorphic to G mod n, but if they're isomorphic, then there is some isomorphism between the two sets. And so it doesn't, because it's an isomorphism, it doesn't matter which direction it's going, because you have isomorphisms in both directions, which cancel each other out to get the identity. And so we'll just say that it's going this way, and this is J. And so what this map does is we take an element of G, we mod out by n, and then we see what that is, what that looks like as an element of H under this isomorphism. Okay? So the other thing to note about this is that this is actually kind of special. There's something special about the short exact sequence, because not only can we go this way, but H is a subgroup of G. So we can actually go back from H to G by the inclusion map. The inclusion map gives us a way to go from H back to G. And so yeah, so that's a neat property, and that turns out to be a really important property. And actually, what we're going to prove next time is that that ability to go from here backwards to here and having this short exact sequence is equivalent to having a semi-direct product. And so I'll leave the details of what I just said for next time.